Okay, as Alon said, I'm Yossi from Neuronic, and what I came to speak about today, most of our work today is in small UAVs and larger drones. Now do you hear me? Okay. I said I'm Yossi from Neuronic. Most of our work today is done with command and control systems on small and larger systems in ground stations and also on the platforms themselves. Everything needed as far as picture identification, tracking, homing, depends what kind of vehicle we're talking about. What I came to speak about today, and these are systems that you could say are standard systems. The everything's ready. The systems are there, many years you could say. And what I came to speak about today is not these systems, but what I see now as the next challenge of systems, and that is combining robotics and ground vehicles inside systems of command and control, including drone command and control systems. So when I build a system that's a tactical system for forward deployed forces that want to control flying vehicles and ground vehicles, what do I need to do? Another important thing is, what do I need to do when I want to be able to control different systems? Today, when I have command centers, I can control different kinds of drones, IAI or Elbit or other companies. But in robotics, many times I can't. Every robot has its own operating system, and it's rare that these systems can talk to each other. Another thing, for many of these systems, there's teleoperations. That means robots or vehicles that respond to a remote control and can think autonomously and add autonomy. So what I came to speak about was first about how robots operate today, command and control systems for robots, and how we can create command and controls that are autonomous without changing the robots in some of the cases. It's easy to say, let's build a new system, replan it, throw everything that we had away, but how can I do this without needing to upgrade the old systems? Can I turn these systems into autonomous tools that can talk to other vehicles without changing them? Because change is very expensive and takes a lot of time. So as I said, we'll start with the challenges that robotic systems have. Vehicles, ground robots, small drones, dogs, underground vehicles. We'll talk about how you implement autonomy. NVIDIA, for instance, tell us this is how you need to implement autonomy. What are the problems that I have in these kinds of vehicles today? Usually that they don't have a brain, or that they have very limited or narrow capabilities, and how I combine them. Then I will talk about how we combine them in C4I systems of drones and UAVs, and architecture that is based on agents to incorporate various tools, not to make a system that's limited to one or two tools, but integrate several and different kinds of tools. So today what happens as far as the challenges is that most of these systems are still teleoperated and not so smart. They rely on the operator, and mostly the operator can't operate more than one robotic ground system. These systems are usually vendor specific. They work on communication between the operator and the vehicle itself, and they don't relay information between vehicles. In addition, the communication itself, the system, the hardware itself, not only the protocols, the hardware can talk to each other. And last, of course, very little onboard compute abilities. How robotic systems work, NVIDIA's recommendation is to incorporate compute systems that are very powerful. These, of course, take a lot of energy. If I make a small robot with a battery, it will drain the battery very fast. Second, if I make robotic tools that need manipulation, for instance, a vehicle that has a robotic arm that's to open a door or put down a payload, or etc., then the operation of this hand autonomously, not by operator, like EOD operators do, requires very powerful computing and very big models. The models that we know today are VLA models that are very heavy. Robots in ground vehicles, full robots, I'm not talking about a little vehicle, require NVIDIA driven tools 100 watts and above. And of course, I can't operate them with small batteries if it's a small vehicle. And so, what is our approach when we try to solve problems like this? The first and foremost, it's to keep the robot unchanged and to transition the computing to the rear. This works when you have a big fleet of robots that I'm not allowed to change or it's too expensive to change. And what we do is we demand that the control system doesn't send digital orders like we do in Mavlink to UAVs, but controls it with remote control to take the command and control module, send orders by the operator. And the second option is, yes, to put a compute on board, but very small, that doesn't take a lot of battery space and not a lot of space, and doesn't need rewiring of the robot. An example, one of the interesting things, many times we look at a robot and we say vehicle, and sometimes you look at a robot and we think about an arm or engines. So I wanted to think about a scenario where I may need both. Example, this is a real example that we have out in the field, a robotic arm by UGV, is unmanned ground vehicle, and it has an arm to manipulate something, for instance, open a door, as I said, and other things, search rooms. Another example, have a robotic dog, quadruped for inspection and manipulation of ID tasks, for instance. And the best example, I think, of combining a vehicle with an arm is an underground excavator. It's an example of something that we did. A small mini excavator. It has tracks. It goes back, right, left, and it also has an arm that needs to be manipulated with various modules of robotics. These models are very heavy, very sophisticated. This is the example. Of course, it's not exactly like this. It looks much smaller. It's smaller than 1 meter. And the demand is to operate more than 6 engines on the arm autonomously, to process simultaneously the LiDAR and various cameras on the vehicle itself in order to navigate, to turn right or left, find the right path. So first, I need a lot of compute, and second, I'm not allowed to use components that will take a lot of compute capability because of space and battery. So how do we do this? First, we have to invent a computer module that's very small. Second, in order to do this, we can't work in a regular way like NVIDIA tells us to do. And in robotics, it's very interesting to know, also for UAVs, the robot model that operate arms say, look at the situation of the hand now and do a prediction of the next situation according to video coming from 2 cameras in different angles. For instance, 1 camera on the arm or on the excavator and 1 from the side. In order to do that, I need to know what the situation of the hand is. I need a brain with a lot of compute. I need a nervous system to tell me what the situation of the hand is. But not only do I have a small brain, I don't have this nervous system inside this robot to know what its own situation is. So what we did is to imitate, to learn what are the movements of the operator under any circumstance, and turn this into autonomous and not according to states. And in this way, we solved this problem also with a small computer and also without rewiring the robot. I gave this example because it's an example that incorporates both uses of robotics, also arm and also vehicle. Of course, it can be done only with a vehicle, and that's easier. Now, I think, how can I combine systems like this inside of command and control systems? Usually C4Is, systems controlling a robot, very similar to UAVs. I have a tablet and I control the robot. Many times I can't control another robot because every one of them is vendor specific and I don't have the ability, they don't speak to each other, not protocol wise and not their communication systems. One has a microARD, the other one has DTC, or another module that doesn't talk to the other. And I want to create a box that will control them and UAVs and have them share information and create autonomy between them. How do I do this? The idea here is based on robotic control that can be done to any robot. We simply adapt it also to UAVs and also to regular robots. It's a known practice in the architecture of NVIDIA. It's LLM MCP, large language model to multi-chip package. It's very known. It's a practice done in industry. Until now, it wasn't done for both drones and robots. We create the LLM MCP system that adapts both. Many protocols today, we can talk about Mavlink, that are both in UAVs and in robots. DDS that is also very more relevant to ground drones. And of course, others are very manufacturer specific. And this is a component that takes metadata from one protocol and adapts it to the other system. Also, to every kind of robot, I have to have an agent that knows how to deal with it. This agent knows how to send it to orders, if it's predefined orders like in Mavlink, or send it remote control orders where I translate what I want to say and I run this locally. And assuming that I have communication with the robot, I run it locally on my control system. The second thing that this box can do is all the video analytics from the various drones on the ground, assuming that they don't have on board their own computing system, geo-registration or finding their own position according to previous data. Also here is something I can run on the system. And also models of robotics in a distance from this box. Usually when we walk on these boxes, we need a control system with servers, with powerful NVIDIA chips, powerful servers to support all these streaming capabilities and functions. When the requirement that we have is to have a tactical box that's carried by hand, several kilograms, and recently such a box was built by NVIDIA called DGX Spark 3 months ago. This box can take 2,000 tops. 2,000 tops, if we think about it, it's more or less what such a box should incorporate in order to manage several streams or less, depending on the service I want to supply. I will cut because there's not a lot of time. Different protocols that it uses. And last thing that I want to explain is how I train such a box and create an ability to add or augment it with other systems swiftly. We use NVIDIA tools. It enables us to simulate physically robotics, including all the, Ross used the physics or the different physics of the different systems to train on synthetic data and also incorporate reinforced learning that's very important for robotics. Other capabilities that it gives us is the ability to simulate a multi-robot environment or multi-drone and robots, that this is a requirement that we have, and in this way to get an entire fleet and check it with autonomous system for the various missions. If you want to see how it looks, our booth is at the end. You can see small robots, simulation abilities, and ask questions. Thank you. Questions?